The question of what constitutes the largest thing in the universe is, on its surface, deceptively simple. It seems like the kind of question that should have a single, clean answer, a name and a measurement, something that can be stated in a sentence and then set aside. But in practice, the question opens into a series of deeper problems that touch on the nature of observation, the limits of physical theory, the meaning of the word thing, and the degree to which human beings can meaningfully comprehend structures that exist at scales so far beyond ordinary experience that even analogies tend to collapse under the weight of the numbers involved. To approach this question seriously requires moving through several layers of understanding, beginning with the objects that are merely large by everyday human standards, and ascending step by step through increasingly vast structures until we reach the boundaries of what can currently be observed, measured, or even coherently defined. The Earth, to begin at a familiar scale, has a diameter of roughly 12,742 kilometers. This is a number that most people can at least partially grasp by analogy with distances they have traveled or seen on maps. But even this relatively modest cosmic object is already beyond direct human perception in its totality. No individual standing on the surface of the Earth can see the whole planet at once. The curvature of the surface was inferred long before it was directly observed, and the full shape of the Earth was not photographed until the middle of the 20th century. This is worth noting because it establishes a principle that will become increasingly important as we ascend in scale. At every step, the structures being described become harder to perceive directly, and the means by which we know about them become more indirect, more dependent on chains of inference, and more shaped by the instruments and theoretical frameworks available at a given time. Jupiter, the largest planet in our solar system, has a diameter of approximately 139,820 kilometers, roughly 11 times that of the Earth. Its volume could contain more than 1,300 Earths. The Sun, in turn, dwarfs Jupiter. The Sun's diameter is about 1,392,000 kilometers, roughly 10 times that of Jupiter and about 109 times that of the Earth. Its mass is approximately 333,000 times the mass of the Earth, and accounts for about 99.86% of the total mass of the solar system. These numbers are already difficult to hold in the mind in any visceral way, but they are still within the range of what can be expressed using familiar units. The Sun is large, but it is a fairly ordinary star. It belongs to the category known as G-type main sequence stars, and there are many stars that are significantly larger. Among the largest known stars is UY Scuti, a red supergiant located in the constellation Scutum, roughly 5,700 light-years from Earth. Estimates of its radius have varied as measurement techniques have improved, but it is generally placed at around 1,700 times the radius of the Sun. If UY Scuti were placed at the centre of our solar system, its surface would extend beyond the orbit of Jupiter. Another candidate for the title of largest known star is Stephenson 218, also a red supergiant, with an estimated radius of approximately 2,100 solar radii. These measurements carry significant uncertainty because the stars in question are far away, embedded in dusty regions of the galaxy, and their apparent sizes can be affected by surrounding nebulosity. The precise ranking of the largest stars changes as new observations refine earlier estimates, which is itself a useful illustration of how knowledge at these scales is always provisional, always contingent on the sensitivity and resolution of the instruments used. But even the largest stars are, in the context of the universe, relatively small objects. A star, no matter how enormous, is a single gravitationally bound body. The next step up in scale involves systems of stars, and the most immediate example is a binary or multiple star system, in which two or more stars orbit a common centre of mass. These systems can span distances measured in astronomical units, where 1 astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. Some wide binary systems have separations of thousands or even tens of thousands of astronomical units, but these are still relatively compact structures. Moving further up in scale, we encounter star clusters. Open clusters, like the Pleiades, contain a few hundred to a few thousand stars and span regions of space, on the order of 10 to 30 light-years across. Globular clusters are denser and older, typically containing hundreds of thousands of stars packed into roughly spherical regions that may be 100 to 300 light-years in diameter. Globular clusters are among the oldest structures in the universe, with many dating back more than 10 billion years, and their study has been instrumental in establishing the age scale of the cosmos. Beyond star clusters, the next major structural category is the galaxy. The Milky Way, our own galaxy, is a barred spiral galaxy with a disk diameter estimated at roughly 100,000 to 180,000 light-years, depending on where the boundary is drawn. This boundary is itself somewhat arbitrary, because galaxies do not have sharp edges. The density of stars decreases gradually with distance from the centre, and the outermost regions of the stellar disk merge into a diffuse halo of old stars, globular clusters, and dark matter that extends much farther still. Recent studies using data from the Gaia Space Observatory and other surveys have suggested that the Milky Way's stellar disk may be somewhat larger than previously thought, with warps and flares in its outer regions that complicate simple measurements of its diameter. The Milky Way contains somewhere between 100 billion and 400 billion stars, a range that reflects both genuine uncertainty and the difficulty of counting objects that are often too faint to detect directly. It also contains large quantities of gas, dust, and dark matter. The dark matter component is particularly significant because it accounts for a large fraction of the galaxy's total mass and extends well beyond the visible disk in a roughly spherical halo. Estimates of the Milky Way's total mass, including dark matter, range from about 1 to 2 trillion solar masses. The Milky Way is not an unusually large galaxy. It is moderately sized within the context of known galaxies. The Andromeda Galaxy, also known as Messier 31, is somewhat larger in terms of its disk diameter, and was long thought to be significantly more massive, though more recent studies have suggested that its total mass may be comparable to, or even somewhat less than that of the Milky Way. The largest known galaxies are far bigger than either of these. IC 1101, an elliptical galaxy located at the centre of the Abell 2029 galaxy cluster, has an estimated diameter of roughly 4 million light-years, though this figure depends on the surface brightness threshold used to define its extent. IC 1101 contains several trillion stars and is one of the most massive galaxies ever observed. However, even a galaxy like IC 1101, vast as it is not the largest category of gravitationally bound structure. Galaxies tend to exist in groups and clusters. The Milky Way belongs to a small collection of galaxies known as the local group, which contains more than 80 known galaxies spread across a region about 10 million light-years in diameter. The local group is dominated by two large spiral galaxies, the Milky Way and Andromeda, with the rest being smaller satellite galaxies, dwarf galaxies, and irregular galaxies. The local group is itself a relatively modest structure. Much larger collections of galaxies exist in the form of galaxy clusters. A galaxy cluster is a gravitationally bound collection of hundreds to thousands of galaxies, along with large quantities of hot intracluster gas and dark matter. The Virgo cluster, the nearest large galaxy cluster to the local group, contains more than 1,000 galaxies and spans a region roughly 15 million light-years across. The Coma cluster, another well-studied example, contains over 1,000 large galaxies and many more smaller ones, spread across a region roughly 20 million light-years in diameter. The total mass of a large galaxy cluster can reach 10 to the 15th solar masses, or about a quadrillion times the mass of the Sun, with the majority of that mass in the form of dark matter. Galaxy clusters are among the most massive gravitationally bound structures in the universe, and this is an important distinction. The phrase gravitationally bound means that the components of the structure are held together by their mutual gravitational attraction and are not being pulled apart by the expansion of the universe. This distinction matters because, at scales larger than galaxy clusters, the expansion of the universe becomes the dominant factor, and structures at those scales are not gravitationally bound in the same sense. They are not stable, self-contained systems. They are patterns in the distribution of matter that are being shaped by both gravity and cosmic expansion simultaneously. The next step up in scale from galaxy clusters is the supercluster. A supercluster is a large region of space that contains multiple galaxy clusters and groups, connected by filaments of galaxies and gas. The local group, for example, is part of a structure known as the Laniakea supercluster, which was defined in 2014 by a team led by R. Brent Tully, using a method based on the analysis of galaxy velocity flows. The Laniakea supercluster spans approximately 500 million light-years, and contains roughly 100,000 galaxies with a total mass of about 10 to the 17th solar masses. Its name comes from the Hawaiian words for immense heaven. The definition of Laniakea was based on a particular method of identifying coherent velocity flows in the local universe. The idea is that within a supercluster, galaxies are generally moving toward a common centre of gravity, known as the Great Attractor. Rather than simply receding from each other as they would if only the Hubble flow, the overall expansion of the universe were acting on them. The Great Attractor is located roughly 250 million light-years from Earth in the direction of the Centaurus and Norma constellations, and exerts a gravitational pull on a large volume of surrounding space. The exact nature of the Great Attractor is still debated. It does not correspond to a single object, but rather to a large concentration of mass, including galaxy clusters and the intervening matter between them. The definition of superclusters is, however, somewhat fluid. Different researchers have used different criteria to define them, and the boundaries of superclusters depend on the method of analysis. Some definitions are based on galaxy density, others on gravitational potential, and others on velocity flows. The Laniakea definition using velocity flows has the advantage of providing a physically meaningful boundary, the surface beyond which galaxies are no longer falling inward, but are instead being carried away by the expansion of space. But it also means that Laniakea is not a gravitationally bound structure in the traditional sense. Over time, most of its component parts will not remain together. The individual galaxy clusters within Laniakea are gravitationally bound, but the supercluster as a whole is not. This brings up a fundamental issue in discussing the largest structures in the universe. At scales above roughly 10 to 20 million light-years, the expansion of the universe begins to dominate over gravitational attraction. Structures at these scales are not permanent. They are transient features of the large-scale distribution of matter shaped by the initial conditions of the universe and the interplay between gravity and expansion. They are real in the sense that they can be observed and measured, but they are not things, in the same sense that a star or a planet or even a galaxy cluster is a thing. They are patterns, arrangements, configurations. This does not make them unimportant. Quite the contrary. The large-scale structure of the universe, the arrangement of galaxies and galaxy clusters into filaments, walls, sheets, and voids, is one of the most important observational constraints on cosmological models. It encodes information about the initial density fluctuations in the early universe, the nature of dark matter and dark energy, and the physical processes that govern the growth of structure over cosmic time. The large-scale structure of the universe is often described using the metaphor of a cosmic web, though the term metaphor is slightly misleading because the structure really does resemble a three-dimensional web or foam in many of its properties. Galaxies are not distributed uniformly through space. Instead, they're concentrated along filaments, elongated structures that can stretch for hundreds of millions of light-years. These filaments connect denser nodes, which correspond to galaxy clusters and superclusters. Between the filaments lie vast, nearly empty regions known as cosmic voids. The walls and sheets of galaxies form the boundaries of these voids. The discovery and mapping of this large-scale structure has been one of the major achievements of observational cosmology over the past several decades. Early galaxy redshift surveys in the 1980s, such as the CFA redshift survey conducted by Margaret Geller, John Huchra and their collaborators, revealed the first clear evidence of large-scale patterns in the distribution of galaxies. One of the most striking features discovered in this survey was the Great Wall, also known as the CFA-2 Great Wall, a vast sheet-like concentration of galaxies extending at least 500 million light-years in length, roughly 300 million light-years in width, and about 15 million light-years in thickness. It was, at the time of its discovery, the largest known structure in the universe. Since then, larger structures have been found, as surveys have covered greater volumes of space with increasing completeness. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, is a massive filamentary structure approximately 1.37 billion light-years in length, making it roughly 3 times as long as the CFA-2 Great Wall. It is located at a distance of approximately 1 billion light-years from Earth. Like the CFA-2 Great Wall, the Sloan Great Wall is not a single, coherent, gravitationally bound object. It is a pattern in the distribution of galaxies, a concentration of matter along a particular direction that stands out against the background of the cosmic web. Even larger structures have been identified in more recent years, and each new discovery has raised important questions about the consistency of these structures with the standard cosmological model. One such structure is the Hercules Corona Borealis Great Wall, first reported in 2013 by a team analysing the distribution of gamma-ray bursts detected by the Swift and Fermi satellites. This structure, if confirmed, would span approximately 10 billion light-years, making it the single largest feature ever identified in the observable universe. Its existence has been the subject of considerable debate. Some researchers have questioned whether it is a genuine physical structure or a statistical artifact resulting from the limited number of gamma-ray bursts available for analysis, and the particular methods used to identify clustering. The significance of these very large structures lies partly in their potential to challenge the cosmological principle, which states that the universe, when viewed on sufficiently large scales, is homogeneous and isotropic, meaning that it has the same statistical properties in every direction and at every location. This principle is a foundational assumption of the standard model of cosmology, the lambda-CDM model, which combines general relativity with cold dark matter and a cosmological constant, lambda, to describe the large-scale evolution of the universe. If structures exist that are significantly larger than the scale at which the universe is expected to become homogeneous, typically estimated at about 300 to 400 megaparsecs, roughly 1 billion to 1.3 billion light-years, then this would potentially violate the cosmological principle and require revisions to the standard model. The homogeneity scale is not a sharp boundary, but rather a statistical concept. Below this scale, the distribution of matter is clearly inhomogeneous, with clusters, voids, filaments, and walls creating a complex pattern. Above this scale, the statistical properties of the matter distribution are expected to be approximately the same regardless of where one looks. The existence of structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, if they are real and coherent, would suggest that the homogeneity scale is larger than currently estimated, or that the standard model's predictions about the growth of structure need to be modified. It is worth pausing here to consider the methods by which these large structures are detected, because the reliability of any claim about the largest structure in the universe depends critically on the quality and interpretation of the observational data. Galaxy redshift surveys, such as the Sloan Digital Sky Survey and its successors, measure the redshifts of millions of galaxies to construct three-dimensional maps of the galaxy distribution. Redshift in this context refers to the stretching of light from distant galaxies caused by the expansion of the universe, and it serves as a proxy for distance, with greater redshift corresponding to greater distance, though the precise relationship between redshift and distance depends on the cosmological model assumed. These surveys have been enormously successful in mapping the cosmic web at distances up to a few billion light-years, but they become increasingly incomplete at greater distances because the galaxies are fainter and harder to detect. At very great distances, other traces of the matter distribution are used instead of individual galaxies. Quasars, which are extremely luminous active galactic nuclei powered by supermassive black holes, can be detected at much greater distances than ordinary galaxies and have been used to probe the large-scale structure at redshifts of 2, 3, or even higher, corresponding to times when the universe was less than a quarter of its current age. Gamma-ray bursts, the most energetic explosive events in the universe, have also been used as tracers, as in the case of the Hercules Corona Borealis Great Wall. However, these tracers are much sparser than galaxies, and the statistical analysis of their clustering is correspondingly more uncertain. Another important observational tool for studying the large-scale structure of the universe is the cosmic microwave background, the relic radiation from the early universe that was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for neutral hydrogen atoms to form and photons to travel freely through space. The cosmic microwave background has been mapped with extraordinary precision by a series of satellite missions, including COBE, WMAP and Planck, and its tiny temperature fluctuations, on the order of 1 part in 100,000, encode information about the density fluctuations in the early universe that later grew into the large-scale structures we observe today. The cosmic microwave background provides a snapshot of the universe at a single early epoch, and the statistical properties of its fluctuations are consistent with the predictions of the lambda-CDM model to a remarkable degree. However, there have been some anomalies in the cosmic microwave background data that remain unexplained within the standard model. One of the most discussed is the CMB cold spot, a region in the southern sky in the direction of the constellation Eridanus, where the temperature of the cosmic microwave background is anomalously low compared to the surrounding sky. The cold spot spans approximately 5 degrees on the sky and has a temperature decrement of about 70 microkelvin below the average. Several explanations for the CMB cold spot have been proposed. One possibility is that it is simply a statistical fluke, an unlikely but not impossible random fluctuation in the primordial density field. Another possibility is that it is caused by a large cosmic void along the line of sight, the so-called Eridanus supervoid, which would produce a temperature decrement through a mechanism known as the integrated Sachs-Wolf effect. In this scenario, photons from the cosmic microwave background would lose energy as they traverse the void because the gravitational potential of the void changes while the photons are passing through it, due to the accelerating expansion of the universe driven by dark energy. Observations have indeed identified a large void in the direction of the cold spot, with an estimated diameter of roughly 1.8 billion light-years and a significant underdensity compared to the cosmic average. However, there is ongoing debate about whether this void is large enough and deep enough to fully account for the observed temperature decrement, or whether some additional explanation is required. The Eridanus supervoid, if it is indeed a single coherent structure, would be one of the largest known features in the universe, not because it contains a great deal of matter, but precisely because it contains very little. Cosmic voids are the counterparts of the filaments and clusters that make up the cosmic web. They are the regions between the filaments, typically tens to hundreds of megaparsecs across, where the density of matter is well below the cosmic average. The largest voids can span over 300 megaparsecs, or roughly 1 billion light-years. These voids are not empty in the absolute sense. They contain some galaxies, typically small and faint ones, as well as tenuous filaments of gas. But their average density is often less than 20% of the cosmic mean. The existence of large voids is a natural prediction of the lambda-c model. In the early universe, regions of slightly below average density expanded faster than their surroundings because they contained less matter to slow the expansion, and over billions of years these regions grew into the vast underdensities we observe today. The statistical properties of voids, including their sizes, shapes, and abundance, provide important tests of cosmological models and can help constrain the properties of dark energy. Returning to the question of the larger structures, it is necessary to distinguish between several different categories of large-scale features. First, there are gravitationally bound structures, the largest of which are galaxy clusters, with masses of up to about 10 to the 15th solar masses and sizes of up to about 30 megaparsecs. Second, there are superclusters, which are collections of clusters connected by filaments, but not gravitationally bound as a whole. The largest superclusters, like Laniakea, span several hundred megaparsecs. Third, there are the filaments and walls of the cosmic web, which can extend for many hundreds of megaparsecs or even over a gigaparsec. Fourth, there are the voids, which can also be extremely large. And fifth, there are statistical overdensities or patterns in the distribution of matter or radiation that may span even larger scales, but whose physical reality as coherent structures is debated. Among the structures that have been identified as candidates for the largest known structure, several deserve detailed attention. The Huge Large Quasar Group, or Huge LQG, was identified in 2013 by Roger Close and collaborators as a concentration of 73 quasars spanning approximately 4 billion light-years in its longest dimension. If this grouping is a genuine physical structure rather than a chance alignment, it would be one of the largest features in the observable universe, and would challenge the homogeneity scale assumed in the standard cosmological model. However, subsequent analyses have raised questions about the statistical significance of the Huge LQG, suggesting that similar groupings might arise by chance in a random distribution of quasars. The debate over the Huge LQG illustrates a general difficulty in studying large-scale structure. At the largest scales, the number of independent samples available becomes very small, making it hard to distinguish genuine structures from statistical fluctuations. Another notable structure is the giant GRB ring, a ring-like distribution of gamma-ray bursts identified in 2015 by a team led by Lajos Balázs. This feature, located at a distance corresponding to a redshift of about 0.78, has a diameter of approximately 1.72 billion light-years. The team argued that the ring is a genuine large-scale structure based on statistical tests, comparing the observed distribution of gamma-ray bursts to random simulations. However, as with the Hercules Corona Borealis Great Wall, the use of gamma-ray bursts as tracers introduces significant uncertainty, because their number density is low and their spatial distribution is subject to selection effects related to the sensitivity and sky coverage of the detecting satellites. At this point, it becomes important to acknowledge that the identification of very large structures in the universe is at the frontier of observational cosmology, where data are sparse, methods are still being refined, and there is legitimate scientific disagreement about what constitutes a structure as opposed to a statistical fluctuation. The standard model of cosmology makes specific predictions about the maximum size of coherent structures, and these predictions are based on well-tested physics, including the growth rate of density perturbations under gravity, the expansion rate of the universe, and the properties of dark matter and dark energy. If some of the claimed very large structures are confirmed, this would not necessarily overturn the standard model, but it would require careful examination of the model's assumptions, and might point to new physics or new aspects of the initial conditions of the universe. Now, setting aside the question of the largest structures composed of ordinary and dark matter, there is a separate and in some ways more fundamental question about the largest possible thing in the universe, the observable universe itself. The observable universe is defined as the region of space from which light has had time to reach us since the Big Bang, accounting for the expansion of space during the light's travel time. The current radius of the observable universe is approximately 46.5 billion light-years, which may seem paradoxical given that the universe is only about 13.8 billion years old. The resolution of this apparent paradox lies in the expansion of space. Light emitted by distant objects when the universe was young has been travelling toward us for billions of years, but during that time the space between us and the source has been expanding. The objects that emitted the light we are now receiving are currently much farther away than they were when they emitted the light. The co-moving distance to the edge of the observable universe, which accounts for the expansion, is about 46.5 billion light-years in every direction, giving the observable universe a diameter of approximately 93 billion light-years. The observable universe is estimated to contain on the order of 2 trillion galaxies based on extrapolations from deep survey data, though this number has been revised several times as observations and counting methods have improved. An earlier estimate based on Hubble Space Telescope data suggested about 200 billion galaxies, but a 2016 analysis by Christopher Consolis and collaborators used a theoretical framework for the merger history of galaxies to argue that the total number, including many small and faint galaxies that are below current detection thresholds, is likely an order of magnitude higher. The total number of stars in the observable universe is correspondingly estimated to be on the order of 10 to the 24th power, or roughly a trillion, though this too is an extrapolation subject to significant uncertainty. The observable universe is not a physical object with a boundary in the usual sense. Its edge, known as the particle horizon, or the cosmic light horizon, is not a wall or a barrier. It is simply the distance beyond which light has not had time to reach us. Objects beyond the observable universe almost certainly exist, according to the standard model, but we have no way of observing them directly. The light from those regions has not yet arrived, and due to the accelerating expansion of the universe driven by dark energy, some of that light may never arrive. The observable universe is, in this sense, an epistemological boundary rather than a physical one. It defines the limits of what we can know through observation, not the limits of what exists. The question of what lies beyond the observable universe is, in principle, unanswerable through direct observation, but it is not entirely beyond the reach of theoretical reasoning. The standard model of cosmology, combined with the inflationary paradigm, suggests that the universe is much larger than the observable portion. Inflation is a hypothetical period of extremely rapid exponential expansion that is believed to have occurred in the first tiny fraction of a second after the Big Bang, during which the universe expanded by a factor of at least 10 to the 26th power in a time interval of roughly 10 to the minus 32 seconds. One of the key predictions of inflation is that the universe should be very nearly spatially flat, meaning that the geometry of space on large scales should be Euclidean, and this prediction has been confirmed by observations of the cosmic microwave background with high precision. The Planck satellite's measurements indicate that the spatial curvature of the universe is consistent with 0 to within about 0.5%. If the universe is exactly flat or very close to flat, then it could in principle be infinite in spatial extent. An infinite universe would have no boundary and no centre. Every location in such a universe would be equivalent to every other location, consistent with the cosmological principle. In an infinite universe, the observable universe would be a finite bubble embedded in an infinitely larger space, and the same physical laws and initial conditions would apply everywhere, leading to the same statistical properties of matter distribution at every location. However, a finite but very large universe is also consistent with the observations. If the universe has a very slight positive curvature, corresponding to a closed geometry, it could be finite in volume but without a boundary, analogous to the surface of a sphere but in 3 dimensions. In such a universe, if you travelled far enough in one direction, you would eventually return to your starting point, although the distances involved might be many orders of magnitude larger than the observable universe, making this impossible to verify in practice. Current observational constraints on the curvature of the universe allow for a minimum radius of curvature that is at least several hundred times the radius of the observable universe, but the actual radius could be much larger or even infinite. Some inflationary models predict that the total universe is vastly larger than the observable portion, by factors that defy ordinary comprehension. In these models, the observable universe is an inconceivably tiny fraction of the whole, and the total volume of the universe could be 10 to the power of 10 to the power of some large number, times the volume of the observable universe. These predictions are, of course, untestable by current or foreseeable observational methods, and they raise philosophical questions about the boundary between physics and metaphysics. A prediction that cannot be tested even in principle is, by some definitions, not a scientific prediction at all, though proponents of these models argue that the testable consequences of inflation, including the flatness and homogeneity of the observable universe, provide indirect evidence for the larger framework. There is another sense in which the question of the largest thing in the universe can be approached, and that is by considering not spatial extent but mass or energy content. The most massive individual objects in the universe are supermassive black holes, which reside at the centres of most large galaxies. The largest known supermassive black hole, as of the most recent measurements, is Phoenix A, located at the centre of a galaxy in the Phoenix cluster, with an estimated mass of approximately 100 billion solar masses, or roughly 10 to the 11th solar masses. TON 618, another extremely massive black hole, has an estimated mass of approximately 66 billion solar masses. The supermassive black hole at the centre of the galaxy, Holm 15A, has been estimated at approximately 40 billion solar masses based on stellar dynamics measurements. These objects are extraordinarily massive but physically compact. A black hole's size is characterized by its event horizon, the boundary beyond which nothing can escape. For a non-rotating black hole, the radius of the event horizon, known as the Schwarzschild radius, is proportional to the mass. For a black hole with a mass of 100 billion solar masses, the Schwarzschild radius would be approximately 2,000 astronomical units, or about 300 billion kilometers, which is roughly 50 times the distance from the Sun to Pluto. This is large by the standards of individual objects within a solar system, but tiny compared to the distances between stars. The largest gravitationally bound objects by volume, as opposed to mass, are galaxy clusters. The most massive galaxy clusters can have total masses exceeding 10 to the 15th solar masses and can span volumes of space roughly 10 to 20 megaparsecs across. The intra-cluster medium, the hot gas that fills the space between galaxies within a cluster, is itself an enormous structure, with temperatures of tens of millions of degrees and masses that can exceed the combined stellar mass of all the galaxies in the cluster. This gas emits X-rays and has been extensively studied by X-ray observatories such as Chandra and XMM Newton. There is yet another category of objects that merits consideration in a discussion of the largest things in the universe, and these are the plasma structures associated with active galactic nuclei. When a supermassive black hole at the centre of a galaxy accretes matter at a high rate, It can produce jets of relativistic plasma, material moving at speeds close to the speed of light that extend far beyond the host galaxy. These jets can inflate enormous lobes of radio-emitting plasma in the intergalactic medium. The largest known such structure is Alcyonius, a giant radio galaxy identified in 2022 by Martine Owe and collaborators using data from the LOFAR radio telescope. Alcyonius has radio lobes that span approximately 16 million light-years, or about 5 megaparsecs, making it the largest known structure produced by a single galaxy. For comparison, the distance from the Milky Way to the Andromeda Galaxy is about 2.5 million light-years, so the radio lobes of Alcyonius extend over a distance roughly 6 times greater than the separation between these two galaxies. The discovery of Alcyonius was notable not only for its size, but also because its host galaxy and central black hole are not particularly unusual. The host galaxy has a stellar mass of roughly 240 billion solar masses, and the central black hole has a mass of roughly 400 million solar masses, both of which are well within the normal range for large galaxies. This suggests that the enormous size of the radio lobes is not simply a consequence of an unusually powerful central engine, but may be related to the density of the surrounding intergalactic medium, the age of the jet activity, or other environmental factors. The fact that such an enormous structure can be produced by a relatively ordinary galaxy raises questions about how many similar structures might exist, but remain undetected because they are too faint or too diffuse for current instruments. The physical processes that produce giant radio galaxies involve the conversion of gravitational energy from the accreting black hole into kinetic energy of the relativistic jets, which then deposit their energy into the surrounding medium. The jets can remain collimated, maintaining their narrow beam-like structure, over distances of hundreds of kiloparsecs or even megaparsecs, which requires a delicate balance between the internal pressure of the jet, the magnetic field structure, and the density and pressure of the ambient medium. When the jets eventually decelerate and spread out, they inflate large lobes of relativistic plasma that emit synchrotron radiation at radio wavelengths. These lobes can persist for hundreds of millions of years after the jet activity has ceased, gradually fading as the relativistic electrons lose energy through radiation and expansion. The existence of structures like Alcyonius and other giant radio galaxies also has implications for the broader question of how energy and matter are distributed in the universe. The feedback from active galactic nuclei, including the energy deposited by jets into the intergalactic medium, is now recognized as a crucial factor in regulating the growth of galaxies and the cooling of gas in galaxy clusters. Without this feedback, numerical simulations of galaxy formation produce galaxies that are much more massive and star-forming than those observed in the real universe. The inclusion of AGN feedback in these simulations brings the predictions into much better agreement with observations, but the details of how the feedback operates, how the jets interact with the surrounding gas, and how the energy is distributed on different scales remain active areas of research. Moving from individual structures back to the large-scale distribution of matter, it is worth discussing in more detail how the cosmic web is formed and what determines its statistical properties. The seeds of the cosmic web were planted in the very early universe, during or just after the period of inflation. Quantum fluctuations in the inflaton field, the hypothetical scalar field that drove inflation, were stretched to macroscopic scales by the rapid expansion, and imprinted as tiny density perturbations in the nearly uniform matter and radiation that filled the universe after inflation ended. These perturbations had a characteristic statistical pattern, described as a nearly scale-invariant Gaussian random field, meaning that the fluctuations had roughly the same amplitude on all spatial scales, with a slight tilt towards slightly larger amplitudes on larger scales, and were randomly distributed with a Gaussian, bell curve, probability distribution. After inflation ended and the universe continued to expand and cool, these density perturbations began to evolve under the influence of gravity. Regions of slightly above average density attracted more matter from their surroundings, growing denser over time, while regions of slightly below average density lost matter and became more underdense. This process, known as gravitational instability, is the fundamental mechanism by which all large-scale structure in the universe was formed. The rate at which perturbations grow depends on the density of matter, the expansion rate of the universe, and the nature of the dark matter. dark matter plays a crucial role in structure formation because it does not interact with light or with ordinary matter through the electromagnetic force. It interacts only through gravity and possibly through other very weak forces. Because dark matter does not emit, absorb, or scatter light, it was not affected by the radiation pressure that prevented ordinary matter from collapsing during the early universe, when photons and baryons, protons and neutrons were tightly coupled. Dark matter perturbations therefore began to grow earlier than baryonic perturbations, and by the time the universe became transparent to light at the epoch of recombination, roughly 380,000 years after the Big Bang, the dark matter had already formed a web-like pattern of overdensities and underdensities. After recombination, ordinary matter fell into the gravitational potential wells created by the dark matter, and the first galaxies and stars eventually formed within these dark matter halos. The properties of the cosmic web, including the sizes and masses of galaxy clusters, the lengths and thicknesses of filaments, and the sizes of voids, are determined by the interplay of several factors: the initial spectrum of density fluctuations, the amount and nature of dark matter, the amount of ordinary matter, the expansion rate of the universe, and the properties of dark energy. The standard lambda-CDM model, with its 6 principal parameters, provides a remarkably good fit to the observed properties of the cosmic web, including the 2-point correlation function of galaxies, which describes how the probability of finding a galaxy at a given distance from another galaxy depends on the distance, the power spectrum of the cosmic microwave background, and the abundance of galaxy clusters as a function of mass and redshift. However, the agreement between the model and observations is not perfect, and there are several areas of tension that are actively being investigated. One of the most discussed is the so-called S8 tension, a discrepancy between the amplitude of matter fluctuations inferred from the cosmic microwave background, which probes the early universe, and the amplitude measured from weak gravitational lensing surveys and galaxy cluster counts, which probe the late universe. The CMB-derived value of S8 is slightly higher than the value obtained from late universe measurements, suggesting that the universe may be slightly less clumpy on large scales than the standard model predicts. This tension could be a statistical fluke, a systematic error in one or more of the measurements, or a sign of new physics beyond the standard model. Another area of active research concerns the nature of dark energy, the mysterious component that accounts for approximately 68% of the total energy density of the universe and is responsible for the accelerating expansion. In the standard model, dark energy is described by a cosmological constant, a constant energy density that fills all of space uniformly. This is the simplest possible form of dark energy, and it is consistent with all current observations, but it raises profound theoretical questions about why the cosmological constant has the particular value it does, which is extraordinarily small compared to the values that would be expected from naive quantum field theory calculations. The discrepancy between the theoretical expectation and the observed value, often cited as a factor of 10 to the 120th, is sometimes called the cosmological constant problem, and is one of the deepest unsolved problems in fundamental physics. If dark energy is not a cosmological constant, but instead a dynamical field whose energy density changes over time, this could have observable consequences for the growth of large-scale structure and the expansion history of the universe. Various forms of dynamical dark energy have been proposed, including quintessence models, in which a slowly rolling scalar field provides the dark energy, and phantom energy models, in which the dark energy density increases over time, potentially leading to a catastrophic fate for the universe known as the Big Rip. Current and upcoming observational programs, including the Dark Energy Spectroscopic Instrument DESI, the VERA-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, and the Euclid Space Mission, are designed to measure the expansion history and the growth of structure with sufficient precision to distinguish between a cosmological constant and various forms of dynamical dark energy. The question of the largest thing in the universe is, as this discussion has progressively revealed, entangled with some of the deepest questions in cosmology and fundamental physics. The answer depends not only on what has been observed, but also on how thing is defined, what criteria are used for coherence or boundedness, and what theoretical framework is used to interpret the observations. If we restrict ourselves to gravitationally bound structures, the answer is a massive galaxy cluster, perhaps the El Gordo cluster or the Shapley supercluster's core components, with sizes of a few tens of megaparsecs. If we include structures that are not gravitationally bound but are coherent patterns in the matter distribution, the answer might be the Sloan Great Wall, or possibly the Hercules Corona Borealis Great Wall if its existence is confirmed. If we include individual structures produced by a single source, the answer is currently Alcyoneus, with its 16 million light-year radio lobes. And if we include the observable universe itself as a thing, then the answer is the observable universe with a diameter of 93 billion light-years. But there is a further dimension to this question that has not yet been fully addressed, and that concerns the structures that exist in the universe, but are not made of matter in the conventional sense. The cosmic microwave background, for example, fills the entire observable universe and can be thought of as a single, coherent, all-pervading structure. It is not a material object, but it is a physical entity with measurable properties. A temperature of approximately 2.725 Kelvin, a nearly perfect blackbody spectrum, and a pattern of temperature fluctuations that encodes information about the early universe. In a sense, the cosmic microwave background is the largest thing that we can directly observe, because it fills the entire observable volume. Similarly, the dark matter that pervades the universe can be thought of as a single, interconnected structure. The dark matter web, the network of dark matter halos, filaments, and voids that underlies the visible cosmic web, is continuous and extends throughout the observable universe. It is not a single gravitationally bound object, but it is a coherent physical system whose properties are determined by the initial conditions and the laws of physics. Numerical simulations of dark matter structure formation, such as the Millennium simulation, the Bolshoi simulation, and the more recent Abacus Summit and Ushu simulations, have produced detailed predictions of the dark matter web's properties, including the masses and concentrations of dark matter halos, the statistical properties of filaments and voids, and the evolution of the web over cosmic time. These simulations are among the largest computational projects ever undertaken. The Ushu simulation, for example, modelled a cubic volume of space 2.1 billion parsecs on a side, containing 2.1 trillion dark matter particles, and required approximately 20 million CPU hours to complete. The level of detail in these simulations is extraordinary, resolving dark matter halos down to masses comparable to those of small galaxies and tracking their formation, merger and evolution over the entire history of the universe. The comparison between the predictions of these simulations and the observed properties of the galaxy distribution provides one of the most stringent tests of the lambda CDM model. One of the important results from these simulations is the prediction of the cosmic web's topology, the way in which filaments, walls, and voids are connected and arranged in 3 dimensions. The topology of the cosmic web is a rich source of cosmological information that goes beyond simple 2-point statistics like the correlation function or power spectrum. Higher-order statistics such as the 3-point correlation function, bispectrum, the Minkowski functionals, and the persistent homology of the galaxy distribution can capture aspects of the cosmic web structure that are invisible to simpler measures. These advanced statistical tools are increasingly being applied to observational data from large galaxy surveys, and they are expected to become even more important as the precision of cosmological measurements improves. The relationship between the largest structures in the universe and the fundamental physics that governs them is not merely a matter of applying known laws to large-scale systems. In some cases, the study of large-scale structure has led to the discovery or refinement of fundamental physics. The most dramatic example is the discovery of the accelerating expansion of the universe in 1998 by 2 independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. These teams used observations of distant Type 1 as supernova to measure the expansion history of the universe and found that the expansion has been accelerating for roughly the last 5 billion years. This discovery implied the existence of dark energy and earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics. The accelerating expansion has profound implications for the future of the observable universe and for the larger structures within it. In a universe dominated by a cosmological constant, the expansion will continue to accelerate forever. structures that are not gravitationally bound will be pulled apart by the expansion, and eventually, even gravitationally bound structures will become isolated as the space between them expands beyond the point where light can bridge the gap. In the very distant future, trillions of years from now, an observer in the Milky Way, or whatever remnant of it exists after its merger with Andromeda, would see a sky devoid of other galaxies, because all other galaxies would have receded beyond the observable horizon. The cosmic microwave background would have been redshifted to undetectably long wavelengths, and the evidence for the Big Bang, the expansion of the universe, and the existence of other galaxies would have been erased from the observable sky. This scenario, sometimes called the cosmic isolation, or heat death scenario, is one of the standard predictions for the long-term fate of the universe under the lambda-CDM model, though it is subject to the caveat that our understanding of dark energy may be incomplete. The fate of the largest structures in the universe is thus intimately connected to the nature of dark energy. If dark energy is a cosmological constant, then galaxy clusters will remain bound, but will become increasingly isolated. If dark energy is dynamical and its density increases over time, the acceleration of the expansion could become so strong that even galaxy clusters, galaxies, solar systems, and eventually atoms are torn apart, a scenario known as the Big Rip. If dark energy decays or changes sign, the expansion could slow down and eventually reverse, leading to a contraction of the universe and a big crunch. Each of these scenarios has different implications for the survival and evolution of large-scale structure, and the current observations favour the cosmological constant scenario, but cannot yet rule out some forms of dynamical dark energy. At this point, it is useful to return to the question of definition that has been lurking throughout this discussion. What counts as a thing? In everyday language, a thing is a discrete bounded object with a well-defined identity. A planet is a thing. A star is a thing. A galaxy, perhaps, is a thing, though its boundaries are fuzzy. A galaxy cluster is a thing in the sense that it is a gravitationally bound system with identifiable members. But a supercluster is less clearly a thing, because it is not gravitationally bound, and its boundaries are defined by convention rather than by physics. A filament of the cosmic web is even less clearly a thing, because it is a continuous extended feature with no sharp boundaries. And a void is, in some sense, the absence of a thing, a region defined by what it lacks rather than by what it contains. The difficulty of defining thing at cosmological scales reflects a genuine conceptual challenge. The universe is not a collection of discrete objects floating in empty space. It is a continuous field of matter and energy, with density varying from place to place in a complex interconnected pattern. The objects that we identify, galaxies, clusters, filaments, voids, are features of this continuous field, defined by thresholds and conventions that serve our purposes of description and analysis but do not correspond to sharp physical boundaries. This is not a mere philosophical quibble. It has practical consequences for how we measure and classify structures, how we compare observations to theoretical predictions, and how we communicate our understanding to a broader audience. Consider, for example, the question of how to define the size of a galaxy cluster. One common definition uses the virial radius, the radius within which the average density is a specified multiple of the critical density of the universe, or sometimes of the mean density. The virial radius is a physically motivated choice because it corresponds roughly to the region within which the cluster is in approximate gravitational equilibrium. But different multiples of the critical density give different radii, and the choice of multiple is to some extent conventional. Some studies use R200, the radius within which the average density is 200 times the critical density, while others use R500 or R2500. Each choice gives a different size and mass for the cluster, and comparisons between studies using different definitions require careful attention to these conventions. Similarly, the size of a cosmic void depends on the algorithm used to identify it, and the density threshold used to define its boundary. Different void-finding algorithms can give significantly different results for the same dataset, reflecting genuine ambiguity in what constitutes a void. This is not a failure of the algorithms, but a consequence of the fact that voids, like all features of the cosmic web, are continuous structures without sharp boundaries. With all of these caveats in mind, it is possible to give a provisional answer to the question of what is the largest thing in the universe, while acknowledging that the answer depends on the definition of thing, and is subject to revision as observations and theoretical understanding improve. If thing means a gravitationally bound structure, the answer is a massive galaxy cluster, with a size of roughly 10 to 30 megaparsecs and a mass of up to about 10 to the 15th solar masses. If thing includes coherent but non-bound features of the cosmic web, the answer is one of the very large filamentary structures, such as the Sloan Great Wall at approximately 1.37 billion light-years, or possibly the Hercules Corona Borealis Great Wall at approximately 10 billion light-years, pending confirmation. If thing includes structures produced by a single source, the answer is the radio lobes of Alcyonius at approximately 16 million light-years, and if thing includes the observable universe itself, then the answer is the observable universe, with a diameter of approximately 93 billion light-years. But in each case, the answer is not simply a name and a number. It is a window into the physics and history of the universe, a marker of the processes that have shaped the cosmos from the first fraction of a second after the Big Bang to the present day. The largest structures in the universe are the products of billions of years of gravitational evolution, driven by the initial conditions set during inflation, modulated by the properties of dark matter and dark energy, and sculpted by the complex interplay of gravity, gas dynamics, radiation, and magnetic fields. They are not static monuments but dynamic, evolving systems, growing, merging, and being reshaped by the ongoing expansion of the universe. The study of these structures is also a story of human ingenuity and technological development. The ability to map the cosmic web in 3 dimensions required the development of large-scale galaxy redshift surveys, which in turn required advances in telescope design, detector technology, fiber optic spectroscopy, data processing, and statistical analysis. The ability to detect and characterize the cosmic microwave background required the development of precision microwave radiometers, space-based observatories, and sophisticated data analysis techniques capable of separating the faint cosmological signal from foreground contamination by the Milky Way and other sources. The ability to simulate the formation of a large-scale structure required the development of high-performance computing, numerical algorithms for solving the equations of gravity and hydrodynamics, and theoretical frameworks for connecting the outputs of simulations to observable quantities. Each of these developments has been the work of large collaborative teams of scientists and engineers, building on decades of prior work and drawing on expertise from multiple disciplines. The identification of the Laniakea supercluster, for example, relied on a catalogue of galaxy distances and velocities that had been assembled over many years by multiple research groups using a variety of distance measurement techniques, including the Tully-Fisher relation, a correlation between the rotational velocity of spiral galaxies and their intrinsic luminosity. The measurement of this relation, and its calibration using galaxies at known distances, was itself a major research effort that spanned several decades and involved careful attention to systematic errors and selection effects. The history of our understanding of a large-scale structure is, in many ways, a history of the progressive expansion of the known universe. In the early 20th century, it was not even clear that the Milky Way was not the entire universe. The so-called Great Debate of 1920 between Harlow Shapley and Heber Curtis centered on whether the spiral nebulae observed in the sky were objects within the Milky Way or separate island universes at vast distances. The resolution came in 1924, when Edwin Hubble used Cepheid variable stars to measure the distance to the Andromeda Nebula, and showed that it was far outside the Milky Way, establishing that the universe contained many galaxies beyond our own. This discovery fundamentally changed the scale of the known universe and opened the door to the study of large-scale structure. Hubble's subsequent discovery, in 1929, that galaxies are receding from us at speeds proportional to their distances, the observation now known as Hubble's law, provided the first evidence for the expansion of the universe and laid the observational foundation for modern cosmology. The proportionality constant in Hubble's law, the Hubble constant h0, has been measured with increasing precision over the decades but remains the subject of a significant discrepancy between different measurement methods, a tension known as the Hubble tension. Measurements based on the cosmic microwave background as interpreted within the lambda CDM model give a value of approximately 67.4 km per second per megaparsec, while measurements based on the local distance ladder using Cepheid variable stars and Type 1a supernovae give a value of approximately 73.0 kilometers per second per megaparsec. The discrepancy is statistically significant and has not been resolved by improved measurements, leading to extensive discussion about whether it reflects a systematic error in one or more measurement methods or a genuine failure of the standard cosmological model. The Hubble tension is relevant to the question of the largest structures in the universe because the value of the Hubble constant affects the conversion between redshift and distance, and therefore affects the inferred sizes and distances of all extragalactic objects and structures. A higher Hubble constant implies a younger universe and smaller distances to objects at a given redshift, while a lower Hubble constant implies an older universe and larger distances. The resolution of the Hubble tension may therefore change the inferred sizes of some of the largest known structures, though the fractional change would be relatively modest, on the order of 10%. Beyond the observable universe, there are theoretical constructs that, if they correspond to physical reality, would dwarf everything discussed so far. One such construct is the inflationary multiverse, a consequence of the eternal inflation scenario proposed by Alexander Vilenkin, Andrei Linde, and others. In this scenario, the inflationary expansion of the universe did not end everywhere at the same time. Instead, inflation ended in localized regions, producing pocket universes or bubble universes, each of which undergoes its own Big Bang and subsequent cosmological evolution. The space between these pocket universes continues to inflate, and new pocket universes are constantly being produced. The result is an infinite, ever-growing collection of pocket universes, each potentially with different physical constants and even different effective laws of physics, embedded in an eternally inflating background. If the eternal inflation scenario is correct, then our entire observable universe, with its 93 billion light-year diameter, is merely one pocket universe among an infinite number. The multiverse as a whole would be incomparably larger than any single pocket universe, and indeed the concept of larger may not even be well defined in this context, because the spatial geometry of the eternally inflating background is not the same as the geometry within a pocket universe. The multiverse is a deeply controversial idea within physics. It has been criticized on the grounds that it is untestable, that it does not make unique predictions, and that it represents a retreat from the scientific goal of explaining why the universe has the particular properties it does. Its proponents argue that it is a natural consequence of well-motivated physical theories, including inflation and string theory, and that it provides a framework for understanding the apparent fine-tuning of the physical constants that permit the existence of complex structures and observers. The string theory landscape, another theoretical construct related to the multiverse, posits that string theory admits an enormous number of distinct vacuum states, estimated at 10 to the 500th power or more, each corresponding to a different set of effective physical constants and particle physics. If eternal inflation populates this landscape by producing pocket universes in different vacuum states, then the multiverse would contain an essentially limitless variety of physical environments, most of which would be radically different from ours, and most of which would not permit the formation of galaxies, stars, planets, or life. Our particular set of physical constants would then not require a fundamental explanation, but would be a consequence of selection. We observe the constants that are compatible with the existence of observers. This reasoning, known as the anthropic principle, has a long and contentious history in physics and philosophy, and remains one of the most debated topics in foundational physics. Whether or not the multiverse is real, it represents the logical endpoint of the progression from the question, what is the largest thing in the universe, to the question, what is the largest thing that could exist? If the universe is defined as everything that exists, then the universe itself is, by definition, the largest thing. But if the universe is defined as the region accessible to observation, then the question becomes whether there are larger regions beyond our observational reach, and the answer, according to most current theoretical frameworks, is almost certainly yes. It is worth emphasizing that the progression from planets to stars to galaxies to clusters to superclusters to the cosmic web to the observable universe to the multiverse is not simply a progression in size. It is a progression in the nature of the evidence and the certainty of the claims. Planets and stars are directly observed with high precision. Galaxies are directly observed but with some ambiguity in their boundaries. Galaxy clusters are identified through multiple independent methods, including optical imaging, X-ray emission, and the Sunyaev-Zeldovich effect in the cosmic microwave background. Superclusters and large-scale filaments are identified through statistical analysis of galaxy surveys with increasing uncertainty at larger scales. The observable universe is defined by a theoretical framework that is well supported by observations, but involves assumptions about the expansion history and geometry of the universe. And the multiverse is a purely theoretical construct with no direct observational support. This gradient of certainty is a normal and expected feature of scientific inquiry at the frontiers of knowledge. It does not invalidate the theoretical constructs at the most speculative end of the spectrum, but it does mean that they should be treated with appropriate caution and clearly distinguished from observational facts. The distinction between what is observed, what is inferred, and what is conjectured is essential for maintaining the integrity of scientific discourse, and it is particularly important in popular science communication, where the temptation to present speculative ideas with the same confidence as established facts can be difficult to resist. Returning to the observational realm, it is useful to consider one more category of large-scale phenomena that has been discovered in recent years: the detection of baryon acoustic oscillations in the distribution of galaxies. Baryon acoustic oscillations are a signature of sound waves that propagated through the hot plasma of the early universe before the epoch of recombination. These sound waves were driven by the interplay between the gravitational attraction of dark matter and baryons, and the radiation pressure of photons, which resisted compression. When the universe became transparent at recombination, the sound waves froze, leaving a characteristic scale imprinted in the distribution of matter, corresponding to the distance that sound waves had travelled from the Big Bang to recombination, approximately 150 megaparsecs in co-moving coordinates, or about 500 million light-years. This characteristic scale, known as the sound horizon, appears as a slight excess in the probability of finding two galaxies separated by approximately 150 megaparsecs, compared to slightly smaller or larger separations. The detection of this feature in the galaxy distribution was first reported in 2005 by Daniel Eisenstein and collaborators using data from the Sloan Digital Sky Survey, and it has since been confirmed and refined by numerous subsequent studies. The baryon acoustic oscillation scale serves as a standard ruler, a known physical length that can be used to measure distances in the universe with high precision. By comparing the observed angular size and redshift separation of the baryon acoustic oscillation feature at different epochs, cosmologists can measure the expansion history of the universe and constrain the properties of dark energy. The baryon acoustic oscillation feature is not a structure in the usual sense. It is a statistical feature, a pattern that emerges only when the positions of millions of galaxies are analysed collectively. No individual galaxy or group of galaxies is part of a baryon acoustic oscillation. The feature is a property of the ensemble, a signature of the physical processes that shaped the early universe, preserved in the distribution of matter across cosmic time. In a sense, the baryon acoustic oscillation pattern is one of the largest coherent features in the universe, spanning the entire observable volume and reflecting conditions that prevailed when the universe was less than 400,000 years old. It is a fossil, a relic of the primordial sound waves written in the distribution of galaxies across the sky. The study of baryon acoustic oscillations also illustrates how the concept of large can be applied not only to spatial extent but also to temporal duration and causal reach. The sound waves that produced the baryon acoustic oscillation pattern were set in motion within the first fraction of a second after the Big Bang, propagated for several 100,000 years, and left an imprint that has persisted for more than 13 billion years and is observable across the entire volume of the observable universe. In terms of causal reach, the baryon acoustic oscillation pattern is one of the most far-reaching phenomena known to science, connecting the physics of the very early universe to the distribution of matter in the present day. This brings the discussion full circle. The question of the largest thing in the universe is not a question with a single answer. It is a question that, when pursued carefully, leads through the entire hierarchy of cosmic structure, from planets and stars through galaxies, clusters, superclusters, and the cosmic web, to the observable universe and the theoretical constructs that lie beyond it. At each level, the nature of the evidence changes, the meaning of thing shifts, and the connection to fundamental physics deepens. The largest structures in the universe are not merely big, they are the physical embodiment of the processes that have shaped the cosmos from its earliest moments to the present, and their study provides some of the most powerful tools available for understanding the fundamental nature of space, time, matter, and energy. The progression from the familiar to the unimaginably vast is also a progression in the history of human understanding. Each expansion of the known scale of the universe, from the geocentric cosmos of antiquity to the heliocentric solar system of Copernicus and Kepler, from the Milky Way as the entire universe to the recognition of external galaxies, from the static cosmos of early 20th century astronomy to the expanding universe of Hubble and Lemaitre, from the decelerating expansion assumed for most of the 20th century to the accelerating expansion discovered at its end, has been accompanied by changes in the tools, theories, and concepts available to scientists, and has been followed by new questions that pushed the boundaries of knowledge even further. The tools available today, including wide-field spectroscopic surveys, space-based observatories, gravitational wave detectors, and exascale supercomputers, are vastly more powerful than anything available even a few decades ago, and they are producing data at rates that challenge the capacity of existing analysis methods. The next generation of surveys, including DESI, LSST, Euclid, the Square Kilometre Array, and the James Webb Space Telescope, will map the distribution of matter in the universe with unprecedented precision and completeness, extending to higher redshifts and fainter objects than ever before. These observations will refine our understanding of the cosmic web, constrain the properties of dark energy and dark matter, test the cosmological principle at the larger scales, and potentially reveal new structures and phenomena that are currently beyond our reach. The question of the largest thing in the universe is, ultimately, a question about the limits of the knowable. Every answer to this question is provisional, bounded by the sensitivity of our instruments, the completeness of our surveys, and the validity of our theoretical frameworks. The universe may contain structures that are larger than anything we can currently observe or imagine, and our understanding of what constitutes a structure may itself evolve as new data and new theoretical insights become available. What is certain is that the universe is far larger and far more complex than anything that could be grasped by direct human perception, and that the effort to understand its largest features is one of the most ambitious and rewarding endeavours in the history of science. The interplay between observation and theory that has driven this understanding is not a one-way street. Observations constrain theories, but theories also guide observations by predicting what to look for and where to look. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson was partly serendipitous, but its significance was immediately recognized because it had been predicted by the Big Bang theory. The detection of baryon acoustic oscillations in 2005 was the culmination of a deliberate observational program designed to test a specific theoretical prediction. The discovery of the accelerating expansion in 1998 was unexpected and overturned prevailing assumptions, leading to a fundamental revision of the cosmological model. Each of these discoveries expanded the known scale and complexity of the universe, and each raised new questions that are still being pursued. The structures that have been identified as candidates for the largest in the universe, from the Sloan Great Wall to the Hercules Corona Borealis, Great Wall to the radiolobes of Alcyonius to the observable universe itself, are not isolated curiosities. They are integral parts of a single, coherent physical system, the universe, whose properties are determined by a small number of fundamental parameters, and whose evolution follows the laws of physics as currently understood. The fact that these laws, formulated on the basis of observations made on Earth and in the solar system, can be extended to describe the behavior of matter and energy on the largest conceivable scales is itself one of the most remarkable and non-obvious facts about the universe. There is no a priori reason why the laws of physics should be the same everywhere and at all times, and the discovery that they are, at least within the observable universe, is one of the foundational achievements of modern science. This uniformity of physical law is what makes it possible to speak meaningfully about the largest thing in the universe at all. Without it, the question would be unanswerable, because the behaviour of matter at cosmological distances would be unpredictable and incomparable to behaviour observed locally. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, is both a statement about the distribution of matter and a statement about the universality of physical law, and it is this dual character that gives it its power as a guiding principle of cosmological research. The larger structures in the universe are, in the end, reflections of the universe's own nature, products of its initial conditions, its expansion history, and the fundamental forces that govern it. To ask what the largest thing in the universe is to ask what the universe has made of itself over the course of nearly 14 billion years of cosmic evolution, starting from a state of extraordinary uniformity and simplicity, and arriving at the rich, complex, and awe-inspiring web of matter and energy that we observe today. The answer is not a single number or a single name, but a story of gravity and expansion, of dark matter and dark energy, of quantum fluctuations and gravitational collapse, of galaxies and voids and filaments and walls, of sound waves in the primordial plasma, and the long, slow growth of structure across billions of years of cosmic time.